So I've proven 2 of these to you, right? Do you see how the other 4 would just go the same way, right? So I'm not going to go and do the rest of them.
So what happens to the negative that was in front of the square?
It never got squared because this negative was not with this cosecant, right? Where did that negative come from? This is the derivative cotangent y is negative cosecant squared y. This negative is like a negative 1 sitting out in front the whole time. Right? So it never gets squared, so it's going to give you a negative answer. All right. Now, not going to prove anymore. Now you know that they're right there in your formulas, right? The most important one out of the 6 inverse trig functions, the most important one is the derivative of inverse tangent. All right? So know this one. If you take inverse tangent of x and take its derivative, it's 1 over 1 plus x squared. Or if you wanted to, you could write it the other way on the bottom. You could do x squared plus 1. It doesn't matter because it's addition, all right? Know that one. It's on your formula sheets, right? But I want you to know it in a more general format, okay? Because remember, everything we're doing here, we can also use with the chain rule, right? We have chain rule, product rule, quotient rule. All those rules can now be implemented with these new functions. So I like to really learn it this way. Inverse tangent of a box, right? If you want to take the derivative of inverse tangent of a box, it's going to be 1 over 1 plus whatever that box is squared times the derivative of the box. Because of the chain rule, you have to first do what the derivative of the outer function is. Derivative inverse tangent of something is 1 over 1 plus that something squared. But then you have times the derivative of whatever was there, and that goes on the outside. So let's do an example next to this. What if we wanted to know what the derivative of this was? So as an example, find y prime. If I tell you that y is equal to inverse tangent of the square root of x. Yes?
Are we able to write that down?
Yeah, it's okay if you want to write that down on your formula sheet. That's all right. This one's good. All right, do y'all see that we have y equals inverse tangent of a box right there? What's the box? Square root of x, right? So the derivative of that will be 1 over 1 plus whatever the box was, square root of x, but that's squared, right? That's what's going to happen. Not done, though. Times what? The derivative of the square root of x, which is 1 over 2 root x. We've been through that many times now, right? And that would be the raw derivative. Now, I can square that square root on the bottom, so let me just turn that into 1 over 1 plus x, because that's what happens when I square the square root. And then over here I have 1 over 2 root x. And you could go further. You could put these together by multiplying and distributing through, but I think I'll just leave it like that. So now, the homework for this section is basically a bunch of problems where you have to differentiate, but now there's going to be product rule and quotient rule and chain rule and all this stuff, but now you've got these 6 new functions that have derivatives. So I don't know if y'all are catching on to what we've done here. In the very beginning of when we start, well, once we stepped away from the limit, you know how we got rid of the limit at some point finally? And we said, hey, here are these shortcuts. The first thing we learned with shortcuts was the power rule, right? We said, hey, if we ever have x to a power, we have this formula for finding the derivative. And then after that, we said, oh, if you have a sum or a difference, you can just do them separately, right? And then we said, okay, if you have a product, well, that sucks because then you have to use this product rule, derivative of the first times the second plus derivative of the second times the first, right? And then we did quotient rule, right? And then we did chain rule. Yeah? After we did all the rules, then we started to throw more functions at you. We said, oh, okay, well, remember, sine and cosine tangent, all those from pre-cal? Here are their derivatives. But now you can use them with these rules. And then I said, last class, hey, what about exponentials and logs? Now you can use them with these rules. And now we have 6 new ones, inverse trig functions. What are their derivatives? And now you can use them with these rules. So let me open up the book and just pull out a problem that I think looks nice. Nice in terms of not nice? Yes?
So all the inverse trig functions give you a fraction when you take a derivative?
Well, according to the formulas, yeah, it's going to be like 1 over something or x over something. Yeah. You'll get a ratio, yes. So let's see here. All right, just pulling this out of the book here. How about this one? Y equals cosine inverse of sine inverse of t. Oops. Find y prime. So we're treating t like it's our independent variable. Do y'all see that we have composition? We have cosine inverse, and inside of cosine inverse we have sine inverse. So if I want to take derivative, I first have to start out by looking at this as being cosine inverse of a box, right? What is the derivative of cosine inverse of a box according to your formula sheet? What is it? Negative 1 over the square root of 1 minus x squared in the formula sheet, right? But for us, is it going to be x squared? What is it going to be?
Oh, sine.
It's that squared, right? It's that box squared. Yes?
So all of these can be related back to that tangent one?
All of these can be related. No. This is just a very special one. Just know this one. Moving ahead in Cal 2, you're going to see this a bunch. The others you don't see as much. You see sine inverse a lot, tangent inverse a whole lot. The rest not really that much.
But it's the same how there's...
Yes, it's the same in terms of a box. And do y'all realize this box is just me helping you remember chain rule? That's all it is, right? Tangent inverse of something, the derivative is first the formula for tangent inverse, but then you always have to do chain rule. All right, y'all got that? We're not done, right? Derivative cosine inverse of something is negative 1 over the square root of 1 minus that something squared. Times. Now I'm ready to take derivative of the box. What's derivative of the box? 1 over square root of 1 minus, in this case, it's just t, right? T, but then squared. There you go. That's the raw derivative. See, do y'all remember when we learned chain rule? I said if you can't get chain rule down, it's over, right? It's because it never goes away. The chain rule just is always going to be here. So continue to work, continue to do problems, practice. Let's do another couple of these before we move on. I'm eager to get into the next section, but I want to make sure we see a few of these. How about this one? What if y equals sine inverse of the square root of x plus 1 over x minus 1? And I want you to find y prime. What do you think? First thing we have to do, take derivative of sine inverse of that box, right? What's the derivative of sine inverse of a box? 1 over square root of 1 minus the box squared, right? The box for us is everything you see in red, right? We have to take that and square the whole thing, which is actually good, right? Because the square root's going to go away. So I'm going to put that right here. I'm going to do it a little slower. I'm going to go this, and then squared. Y'all good with that? Done with the sine inverse. Now I have to go look at the box. The box has a square root in it, right? So I have to take derivative of the square root of something. How do I take the derivative of the square root of something? 1 over 2 square roots of the something, right? X plus 1 over x minus 1. Now I've done the square root. Now I move inside, and I can take derivative of x plus 1 over x minus 1, which is going to require quotient. Quotient rule, right? Quotient rule. I'm going to do that over here. I'm going to do a little scratch work on the side here. I still need to take the derivative of x plus 1 over x minus 1, right? Take that derivative. So just do a quick quotient rule. It's the derivative of the top times the bottom minus derivative of the bottom times the top over the bottom squared. What's the derivative of the top? 1 times the bottom, x minus 1, minus derivative of the bottom is 1 again, right? Times x plus 1, all of that over x minus 1 squared. Good. Let's clean that up. On the top we have, let's see, x minus 1, that's this, and then distribute the negative through, minus x minus 1, all over x minus 1 squared. And doesn't that just give me a negative 2 on top? Negative 2 over that. So I'm ready to put it in here. Times negative 2 over x minus 1, that quantity squared. There it is. That's a raw derivative. So again, the moral of the story is we have 6 new functions. But now they are allowed, we can play with them with any sort of function you can come up with, right? You can do some sort of chain rule, quotient rule, product rule, anything you can think of, really. And in the problems in the book, they'll give you some problems to try here, all right? Okay, I want to go back for a moment, back in time, to chapter 2, section 7. I want you to actually see when this might actually become valuable to you, although I'm not sure you'll find the value in this, I don't know. Okay, you all love these related rate problems, right? You loved them. And do you remember the problem with the plane flying overhead? Where is it? This problem right here. This is in your notes. It's on video. You can go back and reference it if you want. Just read it for a second. Tell me if it looks familiar to you. Plane was flying horizontally, altitude, 2 miles, blah, 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 right? Okay, if you look back in your notes, the way we did this is we had a general picture, an instant picture, what we wanted, what we were given. We had an equation, and then we did our implicit. And we solved it, right? The general picture was a plane, which I just put as a dot in the radar station. The plane was flying this way at 600 miles per hour. And what we did to actually figure this out is we drew like this, a right triangle. The plane was 2 miles high. We called this angle theta. And this distance from here to here, does anyone have in their notes, did we call that x? We called it x, right? It was this distance right here. And then at the instant in time, we had this picture. Here, we had this was 2 miles, and we knew the distance between them was 6. That was at the instant in time. And theta was in here. And if you go back, watch the video, or if you have this sort of memory, you'll remember that we didn't know what theta was right away. But we said that since we have this triangle, we could figure out what theta was, if we needed to. What we wanted was d theta dt. And we were given dx dt was the speed of the plane. And we said it was shrinking at 600 miles per hour because as the plane moved across, this point moved across, and that x was getting smaller. That ring a bell? And then we came up with an equation. And this was the part where we said, okay, we need to connect x and theta together off of this picture. And I think we used tangent, if you go back, right? We said, okay, after we talked about it a little bit, we decided, you know what, the best equation for this would be tangent theta is 2 over x, right? That's what we have. It's in your notes, if you take notes. And I believe I multiplied both sides by x first, and then I took a derivative. Okay? So if I multiply both sides by x here, I get this. And that was my equation. And then I did the implicit. I'm going all the way through this because I want to show you the part that's going to be different. All right? So I took that equation, multiplied both sides by x, and now we did the derivative. And I have to use a product rule right here on the left side. So what I got was dx dt times tangent theta plus derivative tangent theta was secant squared theta, but because of chain rule, we have to take derivative of theta, which is d theta dt, and then times x, and then equals 0 because the derivative of the right side was 0. I know I'm talking fast, but that's the product rule, and we've done that problem before. And this is where in the problem we had to look at what we had. And the problem was we didn't know what tangent theta was, and we didn't know what secant theta was. So what we had to do is we had to go to our triangle and figure that out, right? If we would have had what we learned today, this is the way we would, another way you could have done this problem that would have been a little easier. Watch. Keep in mind, in order to solve this problem, we needed to know what tangent of theta and secant of theta was, right? In order to solve it this way. I'm going to go back to the very beginning, right here, when we had our equation. I'm not going to change the equation. That's still the equation. But watch what I do now. I don't want to erase anything. I'm going to take that equation, and I'm going to take tangent inverse on both sides. What happens, what do you get on the left side? Just theta, right? Okay, and on the right side, we have tangent inverse of, I'm going to write this, yeah, I'm going to leave it as 2 over x. Okay.
And then do we use the log?
No log, you don't need log? No. This equation and this equation are equivalent equations, is what I'm getting at. These are the same equations, just written a different way. But the beauty of this one is that now, if I do my implicit on this, take the derivative on both sides with respect to t. What's the derivative of theta with respect to t? D theta dt. Okay, now on the right side, what's the derivative of tangent inverse of something? Well, we just learned this today, right? What is that? 1 over? 1 plus, what's my something? 2 over x. But then that, what? Squared? You with me? I'm not done though, right? Now I need derivative of what's in here. Let me do that over here real quick. That's really 2x to the negative 1, isn't it? That's really what this means. Bring the x up. When you take the derivative of this with respect to t, you first do the power rule. Negative 1 comes out. Negative 2x to the negative 2. You subtract 1 from the power. And then times dx dt. Yeah? And then I'm going to drop that x to negative 2 back down. So this becomes times negative 2 over x squared times dx dt. What's better about this than this? How? Here, we needed to know what tangent theta and secant theta was, right? So we had to go to that triangle and figure it out, didn't we? And then we could solve for d theta dt. We could. But look at this one. It's already solved for d theta dt, right? And what is the only thing I need to know? Well, there's two things I need to know to solve it. What? X. Do I know x? Yeah, it was 6 here. No, 6. I would need this side, right? I could get that side pretty easily. And then dx dt I'm given. See, I never need to go and try and figure out what theta is. So it's a little bit, I mean, I'm not saying it's like monumentally better, but you should have that kind of in your mind that, you know what, anytime I have a trig equation, I can always use the inverse now and maybe use the derivative of the inverse instead of the derivative of the trig function. Okay. One more example, and then we're going to move on. All right, I'm going to do this one by drawing a picture on Desmos first. I think in Desmos you have to put arctan. Let's see. Arctan x. Maybe not. Okay. Oh, ACR, yes. There we go. All right, that's not a circle, is it? No. Okay, let me see if there we go. All right, I'm making this problem up. So what I'd like to do here is I'd like for us to, if we're given tangent inverse of x plus y equals x squared plus y squared minus 3, I would like for us to find the equation of the tangent line at the point 0, 2. Now, you should be able to tell me that answer just by looking at that, because I've already given you the graph. Go to the point 0, 2. And the tangent line looks like it's this, right? So the slope is going to be what? 0. So what's the equation of that line? It goes through where? 2. So y equals 2 should be the equation of that line. The slope is 0, right? But the equation of the line is 2. Y equals 2. Let's see if we can get that without that picture, right? Can we figure out that the equation of that tangent line is y equals 2? All right, so first thing I need is I need to know what the derivative is, right? I need a formula for the slope of the tangent line. Unfortunately for this equation, I can't solve for y, so I have to use implicit differentiation. Right, I'm going to take that equation. I'm going to do the derivative with respect to x on the left. Right? And then equals the derivative with respect to x on the right. Now we're going to just play the same game we've been playing. Y'all see that we have tangent inverse of something, right? Tangent inverse of something. So the derivative of that would be 1 over 1 plus x plus y, that quantity squared, right? That's the derivative of our tangent of something. 1 over 1 plus that something squared times, good. Now the derivative of what was in here, right? The derivative of the x plus y, which I can do those separately because there's addition, right? So in parentheses, because it's two terms, I have derivative with respect to x of x, which will turn into a 1, and then the derivative with respect to x of y, which will be dy dx, which is what I'm actually solving for. Am I done on the left? Yes, right? I've taken derivative there. Okay, on the right, I can do each one of these separately, right? I'm going to go a little faster on this one, all right? I should just get 2x plus 2y dy dx, and then minus 0. So I did power rule on each of those, right? 2 came down, 2 times x, and then derivative of x with respect to x, which was 1. And then the 2 came down, 2y, and then derivative of y with respect to x, which was dy dx. And then derivative of negative 3 is 0. Do y'all agree with that? Okay, I'm going to just save myself a little time here. That's really a what? 1. Okay, that was really a 1. Okay, at this point, I am not going to go solve for dy dx. I'm not going to go try and get it by itself yet. What I'm going to do is use the fact that I can replace x with 0 and y with 2. Right now, I can do that. Okay, so at this point, at the point 0, 2, we get this. We get 1 over 1 plus, let's see, what is that? 0 plus 2? Right, it's going to be 2 squared times, let's see, 1 plus dy dx. That, I don't know what that is. And then equals over here 2 times 2 times 0, right? And then plus 2 times dy dx. What's that first fraction become? 1/5? 1/5. And then times 1 plus dy dx equals over here, what do we get? 4 dy dx. You got to distribute that 1/5 through first, don't you? Okay, so let me continue. This is going to be, okay, this is going to be 1/5 plus 1/5 dy dx equals 4 dy dx. Let's get all our dy dx's on one side. So how would I do that? Subtract, right? Subtract the 1/5 dy dx. We have a couple of options here. 1/5 equals, I've got 4 dy dx minus 1/5 dy dx. How many fifths is that when you take 4 and subtract 1/5? 19 fifths? Or you get a common denominator here. 20 over 5, subtract 1 over 5, you get 19 over 5. So 1/5 equals 19 over 5, what? Dy dx. What can I do now to get dy dx over by itself? Divide by 19 fifths or multiply by the reciprocal. What does it turn out to be? Dy dx is what? What is it? I don't want the decimal. Give me it as a fraction. 1 over 19. 1/19. Oh, shit. What was it supposed to be? What was the slope supposed to be? No, that was the equation. What did the slope, what did we say? 0. Wasn't that a guess? Wasn't that, it looked like 0, didn't it? It looks like 0, but is it? It's not 0. You see? It's not a perfect circle. So this is a good example of where your eye might be telling you one thing, like, yeah, that did look like the slope is 0, right? Right? And if you just graphed it, you would maybe conclude, oh, that answer, I know the answer without doing any calculus. But actually, there is a slope there. It's very hard to see it. But the slope of the tangent line at this point is actually 1/19, just a slight slope. You go, put a point here, go up 1, go over 19, right? And draw a line. It's almost horizontal, but it's not quite. We haven't answered the question, have we? That's just the slope. Does anyone have any questions up to that point, though? No? Equation of the line. Here we go. Here's my point. There's my slope. I go back to the point slope formula. Right? So here's the equation. It's going to be, I'm going to put it up here. It's going to be y minus what? 2. Right? Y minus 2 equals the slope, 1 over 19. 1 over 19. And then x minus 0, which is just x, right? There it is. That is the equation of the line that is tangent to that curve at that point. And now I'm going to verify it by graphing it. So y minus 2 equals, I'm just going to put x over 19. There it is. We have a bigger problem. What's the bigger problem? What's the bigger problem? The 0.02 is not on the curve, right? Which is that's a bigger issue. All right, so you get the idea, yes? You get, the whole point of this was just to get the idea of how you do an implicit differentiation, right? How you do that with a new inverse trig function. Okay, on your homework for this, we're done. On the homework, I believe it's, let me see, let me check it. 1 through 6. So look, on 1 through 6, right, inverse trig, 1 through 6. 1 through 6 is a revisiting of pre-cal. And I've talked nothing about the problems 1 through 6. That's just to see if you can get brushed up on some ideas from pre-cal. So if you have trouble with those, ask, all right? But you're probably not going to find anything. I don't know if my videos include that. They may. But 6 through 27, sorry, 16 through 27, those are all just derivative stuff, all right? Also, you should throw on there number 32. It's not on there for some reason. But look at number 32 as well. Okay. That's it. Inverse trig, we're done. We're moving forward. What did you say?
She said we're done.
We're done. Yeah, holiday. We'll come back after the holiday. No, wait, hold on. We already had the holiday.
Yay.
So now we are officially now where we're supposed to be, okay, for today. 3.7. We're skipping 3.6. 3.6 has to do with hyperbolic trig functions. So just so you're aware, there's going to be another 6 trig functions that you've never learned before called the hyperbolic trig functions. And each one of those 6 hyperbolic trig